2211 Lab 3 Black Hole. So in this lab, it's divided into two parts. In part one, we want to determine the mass of a black hole using a GlowScript computational model of a star's motion. And in part two, we want to determine the initial velocity of a spaceship to avoid the black hole using another GlowScript computational model. And a sneak peek of the results, I found the mass of the black hole to be this number and the initial velocity of the spaceship to be this vector. So the applied physics principles in this lab are Newton's second law and the universal gravitational force. We know that Newton's second law states that the net force is proportional to mass times acceleration, or the change in momentum over the change in time. And speaking of dp dt, we can separate it into its parallel and perpendicular components. And furthermore, we know that the final velocity of a system is equal to its initial velocity plus the net force on the system divided by mass times delta t. And for the universal gravitational force, we know the equation to be negative gmm over r squared times r hat. So in part one, finding the mass of the black hole, we know that the system is the star and the surroundings is just the black hole, based on assumptions outlined in Lab 3 instructions. So now we have the model. We know that 2 slides ago, we derived that net force is equal to dp dt, which is calculated up here and then finally equated to here. And then we separate the net force into its parallel and perpendicular components based on the equations right here. So the magnitude would be equal to the parallel component, the perpendicular component, and then the unit vector times ddt of momentum will be the parallel component. And then we solve for the mass of the black hole here, which is basically the gmm over r squared times r hat equation, except we need to solve for m instead of f since we have the net force. So we rearrange the equation to solve for the mass of the black hole. And then to find the average mass, in the loop, I made a total mass variable and a counter variable. The total mass variable adds the total mass of the black hole at each position of the star, and the counter just goes up by 1 every time it makes this calculation, and then the average mass will just be total mass divided by counter. And then I got this as the GlowScript computational model, and if we fast forward a bit, we get a nice orbit, and then we get that the mass of the black hole is this number right here, 9.8 times 10 to the 33rd kilograms, which is shown here with a few more results of the net force and its parallel and perpendicular components. So part 2, don't crash. The system is now the spaceship, and the surroundings are the black hole and the planet that the spaceship takes off from. For the initial conditions, now we take into account the mass of the black hole that we just calculated to be this number, as well as the mass of the planet and the mass of the ship, which are givens. So I have this model here. This is the spaceship trajectory, so it doesn't crash into the black hole, but narrowly misses it because we want to find what's the minimum velocity that it needs to dodge the planet. And then here, again, it's just gmm over r squared. Basically, we want to find the net force on the ship, and the net force on the ship will be the net force, the gravitational force between the ship and the black hole, and the planet and the ship, which are calculated up here using the universal gravitational equation. Potential sources of error: in part 1, we used large delta t values that might result in less accurate average mass calculations. We used days as our delta t values, but if we wanted to be more precise, we could use hours or minutes or even seconds to be more accurate. And then in part 2, we used the plug and chug method of determining the initial velocity, and that'll always be slightly inaccurate. So for the questions, how is the net force and its parallel and perpendicular components different from the rate of change of momentum and its components? Well, mathematically, net force and rate of change of momentum are exactly the same. However, the latter is easier to calculate. Why? So, for net force, we have an infinite number of surroundings exerting a force on the system. So technically, you'd have to take an infinite number of calculations into account, which is, well, impossible. And for the rate of change of momentum, this could be easily calculated using just the object's mass, velocity, and a time interval. And then what initial velocity does the spaceship need to orbit around the black hole? Well, it couldn't be clearly calculated, but this is the number that I got. And based on these calculations, I know that the initial velocity, the exact initial velocity, has to have a lower velocity in the x component than what was found originally and a slightly higher velocity in the y component.